I don't know. For some reason, I just randomly heard that. What? You know.
People talk to my girlfriend on the tires.
Yeah, it's such a random, comment. Hold on.
I got a free drink from the little too. Yeah, she was flirting with me. Best date ever. She was like, "What's your favorite soda?"
Okay. All right. I should mention before we begin, I am aware that I'm a little late or a little deficient in getting the videos uploaded here recently. This week is a particularly hectic week for me in my role as Associate Dean because my job this week is to prepare the list of students that are graduating this spring. So I'm the one who posts the list that says who's graduating and who isn't. So I know there are a few of you who are on that list. So if you're on that list, know that it's your fault. I'm kidding. No, that list is due today, so it's been hectic. We have an unusually high number of graduates this term, which is a good problem to have, but for every one of those students, we have to go through and audit their records, make sure everything's complete, all that. So it just takes a while, is all. Okay. All right. So I'm aware that I'm a little behind on getting the attendance and whatnot up to date. But that'll be a task for this weekend to get everything up to date. My TA's been knocking it out of the park, though, because all the outstanding homework's graded, except for homework 3.4, which was due today. I am hoping that 3.4 was fairly easy, especially in the light of 3.3. Like, if you understood 3.3, 3.4 should have been a breeze. So, did anybody have any questions about 3.4? Straightforward? Okay. Does everybody like the little blue note right here? This one says no homework assigned today. No homework for this weekend. Unless you want one.
No, I'm good.
Oh, are you sure?
Yeah, I'm good.
Okay. I was a little fuzzy on that one, but it seems like there's a consensus that everybody's fine with no work this week. Okay. So today what we're going to do is begin a new topic in the class. Well, it is a new topic conceptually. Like welded connections are certainly do not behave the same as bolted connections. But surprisingly, from a computational standpoint, there is much in common between analyzing and designing bolted connections versus welded connections. For example, in the land of bolted connections, we essentially determine the capacity per bolt, and then we multiply by the number of bolts to get the capacity of a connection, right? Well, in the case of a welded connection, what we'll do is determine the capacity per inch of weld, multiply by the number of inches. So there's that. Another thing is, with bolts, there was the capacity of the bolt and then the capacity of the plate. For this, there's going to be the capacity of the weld metal and the capacity of the base metal. And there's analogies in that regard. So there is a lot that's very common between bolted and welded connections. And that'll be somewhat clear after today. So today what we're going to do is just talk about welding in general, and then we'll spend the latter half of the lecture talking about how you would compute the capacity. We'll come back on Monday and talk about weld limitations, in terms of weld size and weld length, and then we'll get into some examples. Okay, everybody get the code? Okay. So, let's talk a little bit about welded connections. I'm curious, how many of you have ever welded before? I'm just curious. Not easy, is it? It's hard.
Yeah.
Welding, I would say the thing about welding that's worth mentioning, with bolts, theoretically, you could be trained on how to properly install a bolt assembly in the space of 30 minutes. Like, it's not hard, bolt, that's done, right? But welding is an art. Welding takes years to learn and master. It is very difficult to do. It is very difficult to do consistently. I would argue that that's probably one of the greatest hallmarks of a skilled welder is not being able to deposit welds, but be able to deposit them consistently and in a fashion that meets, you know, welding spec. It's one of the reasons why, in terms of the trades, you know, and by trades I'm talking about, you know, carpenters, plumbers, roofers, electricians, things like that, welders are among the highest paid of trades, of folks in the trades, because it is very difficult. It is a learned skill, and it takes a lot of time. So I would definitely, as a structural engineer, keep in the back of your head a latent respect for the folks. So whenever you spec out a welded connection, just recognize that it takes a lot of skill in order to deposit that properly. So I just think that's worth mentioning. Excuse me. So what I'm going to do is I'm going to split this lecture up into sort of, at least when I'm introducing welds, I'm going to split this lecture up looking at sort of two facets of welding. The first thing I'm going to do is talk about the different methods used for welding. So these acronyms, which we'll go through here in a bit, what I'm talking about, for those of you that have welded before, are things like stick welding versus MIG welding versus TIG welding, you know, things of that nature. And then what we'll do is talk about the different welds that we can deposit. So like plug welds, groove welds, slot welds, fillet welds, etc. Okay? So let's talk about the different types of welds that we or the different welding methods that we can use. And the most common, I would say, at least from a structural engineering application, is shielded metal arc welding or stick welding. Okay? I imagine you all have probably heard of stick welding before, okay? But if not, so let's just sort of take a step back and make sure that we all understand what we're talking about with welding in general, okay? So the first thing I want to mention and make sure that everybody is clear about is that welding is not gluing, okay? Gluing, and I know that seems like an elementary thing to say, but I think it's important here to make a distinction. So in the case of gluing or adhesion, what you're doing is, so let's say we're talking about lumber, okay? So with lumber, what you're doing is you have piece of wood A and piece of wood B, okay? And what you're doing is you're introducing a third compound, this adhesive, right? So it was, you know, type bond type 2 or whatever, right? And you slather that between the two panels of wood that you're gluing together, and you press them together, and you essentially create a surface that grips both sides of the wood and adheres them together, okay? So there is still I guess the best way of saying it, there is still sort of like a layer separation between wood, glue, wood type thing. But with welding, that's not the case, okay? With welding, first off, with welding, there's a tremendous amount of energy required, okay? So essentially what you're doing is you're completing a circuit whenever the weld electrode touches the metal, okay? So you have piece of metal A, piece of metal B, and you've layered those on top of one another in some sort of geometry. And then you have one end of your weld machine connected to the workpiece, the other connected to the electrode, okay? So electrode, workpiece, electrode. Once the electrode touches the workpiece, you have essentially completed the circuit, and energy begins to flow, okay? Now, in the case of shielded metal arc welding, what happens is this electrode, which I'll bring some electrodes on Monday so everybody can kind of see it, but this electrode is essentially a consumable piece of metal. And the reason that we call it stick welding is that if you look at the electrode, they're usually about yay long, and they are consumed, and you just keep using them, so they sort of look like little sticks, okay? As you complete the circuit, like I said, there's a lot of energy that's flowing. What you're doing is you're consuming that electrode. You're melting it, okay? And you're melting that electrode, and at the same time you're melting the electrode, you're melting the base metal as well. So you're essentially creating this big molten pool of metal that consists of both the electrode as well as the two pieces that you're welding together. And so once that solidifies, you now have a single unified connection. So that's sort of what makes it different from gluing or adhesion. is that in the case of welding, you're actually melting everything together, okay? Now, how many of you have ever stick welded before? Did I describe that stick accurately? In other words, is it just a piece of metal, or is there something on the outside of it?
It's flux-coated.
There's a flux coating on it. It looks like this granular sand kitty litter type stuff, right? It's just this gritty stuff on the outside, okay? Now, what is that for, okay? So, like I said, what you're doing is you're melting the weld electrode and the base metal, so you're creating this big pool of metal right here. So there's a lot of energy going through right here. What's going to happen is once that electrode is, once the welding process is terminated, that metal's going to want to cool. It's going to want to cool pretty rapidly, okay? What that flux does on the outside, again, it's this like granular coating, kind of looks like this, you know, crusty kitty litter type stuff. What that does is it forms, as you're depositing the weld, it forms this little gas shield right there at the point of connection, okay? What that gas shield is intended to do is prevent impurities from the atmosphere from getting into your welded connection. Probably the biggest impurity that we are worried about in the case of getting into a welded connection is hydrogen, okay? There is ambient hydrogen in the atmosphere, and hydrogen inside a weld is really bad news, because what hydrogen does to a weld is makes it brittle, okay? Hydrogen embrittlement in a weld is really bad, because then it will crack, it will fail. We don't like that, okay? So with welding, at least for the metallurgists and the folks that are designing the electrodes and designing the processes, they sort of have two parallel goals that they need to achieve. For one, they need to design, you know, a weld electrode and a energy process that produces a high quality joint connection. But at the same time, there is a chemistry problem that goes along with it, because they need to produce a protecting gas that prevents hydrogen embrittlement and other impurities from getting into the weld. And so in the case of stick welding, the idea with stick welding is that flux coating prevents hydrogen embrittlement and things like that. Does that make sense? Okay. Now, stick welding is probably the most common application in structural engineering, because one of the things that we are worried about whenever we deposit a weld for structural steel application is weld penetration, okay? And so what I mean by that is, if I have workpiece A and workpiece B and I'm melting them, not only am I melting the electrode, but I'm melting inside the steel plates that I'm welding together. The term weld penetration is how far that energy and that molten metal penetrates into the workpiece. Stick welding is known for getting really good, high quality, deep penetrating welds, which is usually necessary when we have a structural engineering application and we need really strong welds, okay? Now, it's not the only method that we use. Another method that we use is what's called gas metal arc welding. Gas metal arc welding has another name. Another name for it is metal inert gas welding, or MIG welding. Okay, how many of you have ever MIG welded? Okay, so if you've MIG welding is different. Okay, so in the case of MIG welding, we have, instead of a consumable electrode. So one of the downsides of stick welding is you have this stick and you're welding. As you're welding, you consume it, right? And once you get to the bottom, you have to get another one, right? So whenever you're seeing stick welding, they have a big old box of these electrodes, and they keep consuming them over and over and over again. For MIG welding, that's not really the case. The MIG welder has this big spool of continuous electrode, and the weld gun has a little trigger, right? And so you click the trigger, and the weld is continuously deposited. So you can deposit the welds a lot faster, okay? Now, with the downside, you can't get as much weld penetration with the MIG welds. So MIG welds really only work if you need a weld that isn't going to have a high degree of stress on it. So in the case here, we're looking at like a connection plate for a cross frame and a bridge. That's perfectly fine. beam to column type connections in building applications. If they're just regular old floor beam to columns, it's probably fine. Stick welds are usually needed for like groove welds and whatnot, which we'll talk about here a little bit later. Now, the way that you prevent that hydrogen embrittlement is from the gas, right? The term gas metal arc welding or metal inert gas welding. When you ever see a MIG welder, you have the machine that is applying the energy and supplying the electrode, but with that is a big old tank of gas shield, right? Looks like a super huge scuba tank, right? And it contains in it an inert gas such that as you deposit the weld, not only are you feeding this electrode, but you're feeding a gas shield that's spitting out as you deposit the weld, and that's what prevents the embrittlement and whatnot. Does that make sense? Okay. Now, there's a couple other methods worth mentioning. Flux-cored arc welding. I would imagine, how many of you have a garage at home and have like a little MIG welder, a little Lincoln in the back? How many have that? I'm just curious. If you do, if you have like an older sibling or a parent that has a welder in their garage, chances are this is sort of like, I sort of view this as like the hobbyist weld because you don't need a tank, right? The wire, it's basically a MIG welder, but the wire itself contains a coating. The reason I call it sort of the hobbyist welding apparatus is because the setup is particularly small. You don't need some super huge tank. You can do it pretty easily, but you're not going to get super deep penetration on your welds like you would with a stick weld. So just works well. However, there are some good applications in structural engineering, again, as long as you can get the necessary capacity, and that's field welding, because if you're welding in the field, you might be welding outside, maybe, I don't know, on a windy day. If it's windy, a MIG welder with a continuous gas shield isn't really going to work because the wind will just blow it away. So it's a way of getting that. Okay, does that make sense? Okay. Now, I guarantee you, unless any of you worked in a fabrication shop, none of you have ever done this. This is submerged arc welding. Now, this is, I would say, a very much a structural engineering type of weld application, okay? And this is robot welding, is what I would say. Now, the way submerged arc welding works is, well, first off, let's talk about the application. The application is really only valid when you have a long, continuous weld that you want to deposit. So a good example of that would be if you're trying to fabricate a plate girder, right? So a plate girder is different than a W shape. A W shape, it comes out of the mill and it already looks like an I shape. A plate girder, we are taking plate, 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 and welding them together to make an I shape. So the flange and the web are going to be joined by a continuous weld that goes, like 100 feet, if we're talking about a 100-foot plate girder. And so instead of having a human do that, this is where a robot comes into play. And so the robot sort of works in two stages. So one thing it'll do, so it'll deposit both the weld and this granular flux that protects the weld. The actual welding process is submerged under this granular flux. So what will happen is the weld actually occurs under this flux. Again, it looks like this sort of granular kitty litter type stuff that the weld is deposited in. So, and then you can see, they'll suck it back up when it's all said and done. So again, this would only be done in the case of a really, really long continuous weld. You can get pretty deep welds, but you're also limited by your position. You can only weld this way if the weld is flat or horizontal. We'll talk about that here in a second. Okay. Everybody good with this? Okay. So those are the welding methods, the sort of the equipment or the metallurgy side of things. Okay. So utilizing these methods, we would then deposit different types of welds. So I know that maybe there's like a little bit of a confusion between welding methods, welding types, and whatnot. So I think the examples that go along with these would make sense. So for example, the types of welds I'm talking about are things like tack welds, or fillet welds, or groove welds, or plug and slot welds, and things like that. So let's talk about these. Let's talk about first a tack weld. What's a tack weld for? Anybody know why would you place a tack weld?
Keeping things in place.
So it is a initial temporary weld. Okay, that's 100% right. So the idea behind welding is that whenever you weld piece of metal A to piece of metal B, when it's done, it's piece of metal C. It is a unified single product. So you better have your measurements right, like honestly. So the idea behind a tack weld is we clamp our parts together, right? Get the position where we want, and then we'll hit it with a few hits of the weld electrode for like a second or two, just and that's about it. Just to sort of join them temporarily to make sure that our measurements are right. You know, have you heard in carpentry the adage, measure twice, cut once, right? So the idea is measure it, clamp it together, tack it, measure it again before you deposit your full weld. Because if you deposit your full weld and the measurements are off, you're going to have to grind that thing off, and that's going to be a lot of time and a lot of money, right? So the idea is the tack weld is sort of a temporary weld. We don't really design tack welds. That's a fabricator-only process. Okay. What we're going to design are these, fillet welds. Fillet welds are, by and large, the most common structural welds that we see in application, period. Okay? Fillet welds are essentially what happens when you take piece of metal A and piece of metal B and join them by placing a bead of weld along the linear path that joins those together. So the resulting geometry of the weld is sort of triangular. So like in the case of this image here, we have, this, we have this, and then the weld, we sort of assume, looks like that, something about like that, just sort of this triangular bead of weld. And so we call that a fillet weld. I would say that 80 to 90% of the welds that we design and utilize in structural engineering applications are fillet welds. Okay? That's what we use most common. Now, if fillet welds make up the vast majority, the remaining welds are groove welds. Okay? Now, I'll be honest, you probably won't hear many structural engineers or fabricators use the term groove weld. Instead, what they'll probably do is use the term CJP or PJP, either for complete joint penetration or partial joint penetration. So the idea behind a CJP or a PJP weld is if I have plate A and I have plate B, what I'm going to do is join those together by filling the groove in between them with weld metal. So they are a little bit labor intensive to produce. I'll tell you that from a design standpoint, there's not a whole lot that you need to do from a design standpoint, because essentially what you're doing is detailing the welded connection such that, between the two, which would fail, either the weld metal or the base metal. And in the case of these welds, you're detailing them so that the base metal fails first. So you're not having to do a lot of math from a design standpoint. It's not like a fillet weld where you actually have to size things and whatnot. So we won't really talk a lot about groove welds or CJP or PJP because there's not a lot of calc to do. It's mostly just a spec and detailing type concern. Okay. Plug welds and slot welds, I mention them just because you might see them, but they're pretty rare. In the case of a plug weld, what you would do is you would have a hole drilled, or in this case, like 3 holes drilled in a plate, lay that plate on top, and then fill the hole with metal. We don't really do that a lot in structural engineering applications, but we could. Make sense? I should mention something. I actually forgot this on the weld methods, but I should mention this. So I mentioned stick welding, and I mentioned MIG welding. What I am focused on in here are the methods for welding that we would use for structural engineering applications. So, for example, you notice I did not talk about TIG welding, okay? How many of you, if I would imagine most of you who are mechanically inclined probably know what I mean in terms of TIG welding. If you've never heard of it, I'm actually like not that upset, but what I would say is TIG welding and some of these other methods are meant for hyper detailed applications, which would be much more applicable in machine type applications or aerospace type applications. We don't use them for buildings or bridges, so that's why I'm not talking about it. I'm only talking about the stuff that applies to buildings and bridges. Okay. Sorry for that tangent. Let's get back on track. Okay. So we have fillet welds, groove welds, things like that. What about the joints that we can generate? So by joints, what we're talking about is the geometry that would arise from two plates being welded together. The most common ones that we would use for fillet welds are these three, like T's, laps, and corners. And really, for structural engineering applications, I would say this is probably the least common, but T's and laps are much more applicable. Butt joints are going to be much more common in groove weld applications. Edges, I'll be honest, I haven't really seen a lot of applications, practical applications with edges in routine simple structures. Not to say it doesn't happen, but probably the least common of the five that you see here. Okay. Now, one thing that is worth mentioning, at least from a fabrication standpoint, is the welding position, okay? So, whenever you're depositing a weld, okay, one of the things that you want to take into account is the orientation of the piece during weld application. And some of you might be thinking, like, why do I care about this as an engineer? Can't the fabricator just figure this out? For example, if the weld needs to be placed like this, can't the fabricator just flip the piece over? Well, yeah, but how many of you have ever been to a large-scale fabrication shop? If you haven't, what I'll tell you, if I had a weld job on, let's say, a 10-foot deep plate girder, and I'm trying to place a weld between the top flange and the web, just the act of getting that plate girder lifted and flipped into appropriate position, that might seem like, oh, that's just nothing. No, that's a job that requires a significant amount of labor to get it harnessed and strapped up appropriately. The lifting process is a very detail-oriented, gentle application. I mean, steel lifted the wrong way has about as much stiffness as a piece of wet spaghetti. So there's a lot of care that's taken into manipulating pieces in the shop. So it's just something you want to keep in mind. Now, the easiest weld applications are welded this way, like whether they're either flat or horizontal. Some of the welds that I deposited when I was doing my PhD, because I did a lot of lab testing, so I had to do some welding. I had to do, I tried to make sure that a lot of the welds I had to produce were flat or horizontal. I had one weld that I had to produce which was vertical, and man, that was tough. It really was tough to get it right, because what I had to do was I had a beam that I was testing, and I had to weld a stiffener onto it. So I had to, here was the web, and then there was a stiffener that came in, and I had to weld that. Man, that was tough. That was really difficult to place a high quality weld. And I can tell you it was difficult because I didn't place a high quality weld. It was really bad. I got piece of metal A joined a piece of metal B, but it was ugly. I'll just leave it at that. My lab tech helped me. He helped me with that quite a bit. Jerry was a really awesome guy, so I'll just leave it at that. I needed his help that day. Okay. No, excuse me. Part of what I'm going to do in this unit of the class is introduce you to some of the welding symbols and terminology that you will see on drawings. And when I say some, I guess I should be clear, very little, okay? How many of you have ever seen welding drawings? I'm just curious. Because they are confusing sometimes. There's all these symbols and terms, and there's a specific legend and location of how symbols should go, and it can be really complicated. I don't want to turn this into a welding detail class, but I do want you to be able to detail some basic welds. So like I said, what we're going to do is look at fillet welds, and so the only symbols that I care that you have the ability to identify and write are things like this. Okay, so for example, let's take this one here on the left. So if I have a plate and a plate, often on engineering drawings, I will not actually draw the little triangle, okay? Because that doesn't really matter. What matters is this, okay? So what do I have here? I have an arrow pointing to this joint, and there's three things worth mentioning. There's the 1/4, there's this little triangle, and then there's the number 6, okay? So the 1/4 represents the size of the fillet weld. So when I'm talking about size, I'm talking about this dimension and this dimension. So this is the size of the fillet weld right here. And I should have drawn this more like a 45, something like that. So I mean this dimension too. Okay? Now, the 6 refers to how long it is. So if we're talking about, let's say, in 3 dimensions, right? So if I was depositing a fillet weld, it would sort of look something like that, right? So there would be a 1/4 inch weld that's 6 inches long, something about like that, okay? Now, what about the triangles? Okay, so first off, the fact that the symbol is a triangle represents the fact that it is a fillet weld, right? So if you go back here, you have triangles for fillet welds, you have rectangles for plug and slots, groove welds with bevels and all that. So in the case of a fillet weld, it's a triangle. Now, if I have the symbol right here, that means the weld is on the side of the arrow. If the symbol was up here, it'd be on the other side. So like for example, this is a 1/4 inch fillet weld right here, only on the side of the arrow. Over here, because the triangle's on both sides, that means the weld is on both sides of the piece, okay? So those are the only ones that I'm hyper interested that you can interpret, because on most structural fabrication drawings, if you need to interpret welding symbology, if you can interpret this, that's about 90% of the work, okay? Does that make sense? All right. Any questions about sort of the concept of welding, the different methods, the different types, the different joints, different weld positions, all that? Any questions? Okay. Well, like I said, the most common weld application that we utilize in structural engineering is a fillet weld. So let's talk about fillet welds and how we compute the capacity of a fillet weld and look at the specifications a little bit. Okay, so the first thing that we need to talk about when it comes to a fillet weld is a dimension referred to as the effective throat, okay? Now, in reality, if you deposit a fillet weld, okay, so let's talk about reality, okay? So here's a piece, here's a piece, here's a piece, like that, okay? Now, in reality, if you deposit a fillet weld is going to sort of have like, sort of this like rounded bead type geometry. What we're going to do for the purposes of a capacity calculation is we're going to idealize this as a triangle. Specifically, most commonly, a 45-45-90 triangle. So this region right here, we're going to idealize that as the fillet weld, okay? So the size of that fillet weld, I'm going to idealize with this dimension A. I'm going to use A for the size of the weld, okay? Now, whenever we define the capacity of a fillet weld, we define that capacity based on a dimension called the effective throat. And the effective throat is the distance from the root of the weld to the face of the weld, okay? So what we're going to be talking about is this shortest distance right here. That distance is the effective throat, okay? Now, like I said, this is a 45, 45, 90 triangle. That's what we're assuming, okay? So if this right here is a 45, 45, 90 triangle, right? And this dimension is A, then how do I calculate that length right here? How do I figure that out? Okay? Well, I propose that this is just a smaller 45, 45, 90, right? And in the case of this, so now we have this triangle, right? So this is a right angle, this is A, this is 45 degrees. That's the effective throat. Both of these dimensions are going to be the effective throat. So how do I calculate the effective throat? Well, maybe something like, I don't know, the sine of 45 degrees is the effective throat over the hypotenuse, right? Something like that. And so do the math, and you'll get that the relationship between the effective throat and the size of the weld is just 1 over the square root of 2, right? How do I get, that's sine of 45 degrees, right? Okay. So now if you calculate the sine of 45 degrees in your calculator and whatnot, that comes out to about 0.707. So in our capacity expressions we're going to see here in a little bit, you'll see 0.707a. So question, is that 0.707 a factor of safety? No, it's not, right? It's trig, right? It's just trig referencing the difference between the ratio between the size of the weld and its effective throat. It's not a factor of safety, okay? In case I ever asked that on a celebration or something. Now everybody starts writing something down. That was a joke, not wrong. Okay. All right. Okay, so let's talk about the capacity of the joint, okay? So if we open up the spec, we're going to be doing some page flipping here in the spec, but like I said, we're in Chapter J. We've been in Chapter J for a little while. So if you go by the way Chapter J is organized, Chapter J.3 is the section on bolts. We've been in J3 for a little while. What about J2, okay? So let's talk about J2, okay? So what do we have here? We have the design strength of a weld is as follows, okay? We look at the base metal, we look at the weld metal, okay? Now, essentially, so, and unfortunately, this is just sort of how Chapter J2 is referenced. And again, I've talked about this before, how in the specification you have to do a lot of page turning. So but I'll do my best to guide you through it. Okay. So when we look at the capacity of a fillet welded connection, we have to ask ourselves which is going to fail first, the weld metal or the base metal. Now for the base metal, we say that the capacity equals some limiting stress times some area. And I'm saying some limiting stress times some area because we're going to define that more rigorously here in a bit. But what about the fillet welds? Well, for fillet welds, it's some limiting stress times some area. Now there's this term right here. We're going to take that term to be 1, but essentially that accounts for the angle at which the load is applied. What we're going to do is assume the worst case scenario and say that KDS is 1. Depending upon the angle in which your load is applied, you can actually increase your capacity, but we're going to assume the worst case scenario that it's applied the worst way. Okay. Now, if you'll notice, values for all this stuff are in table J25. So if we go to J25, J25 is a pretty big table, okay? So it goes across a couple different pages, okay? So, excuse me. So if you look at table J25, there's going to be headings like plug weld, slot weld, groove welds, and so on and so forth. And if you look at the next page, there's a heading for fillet welds, Okay? So let's look at fillet welds. All right, so we have our fillet weld. We're going to assume that the loads are being resisted in shear. That goes along with that KDS equals 1. That's sort of the worst case scenario. And if we have a fillet weld, we have to consider either the base metal or the weld metal. Now, what does it say for the base metal? It says governed by J4. We'll talk about J4 here in a second. Let's do weld metal first. So what do we know? We know the phi value is 0.75, okay? What about the capacity of the weld? So in other words, like the weld metal itself, the weld electrode, how do we calculate the nominal capacity of that from a stress standpoint? Well, we take 0.6 times FEXX. So what's FEXX? FEXX is the weld electrode strength. I'll bring some weld electrodes in class on Monday. But whenever you purchase like a stick weld and whatnot, the stick weld will have a specification. So like for example, let's say that you buy an E6011 electrode, okay? So what do we have here? So the 60 refers to the tensile strength of the electrode. So in other words, an E60 has an electrode strength of 60 KSI, okay? 70 is probably the most common that we'll use, but 60, 70, 85, something like that, okay? What about the, okay, so E6011, so 60 is the tensile strength. 1 refers to what welding position can you use. So in other words, is this a flat weld, horizontal weld? In the case of an E61, that's all positions, okay? And then the E60, the second one refers to special characteristics like the type of welding machine, the type of flux, so on and so forth. For the purposes of a strength calculation, the only thing we care about is the first 2 numbers. So a lot of the problems that we'll do, I'll say, design this weld using E70 electrodes or E80 electrodes. And if that's the case, then if I said E70, the electrode strength is 70 KSI. Now, the electrode strength is a tensile strength, right? So if it's the electrode strength is 70 KSI, why am I doing 0.6? Because I'm assuming it's in shear. Remember, I told you that whenever we see things in shear, we're going to see that 0.6 pop up. That's what's going on here, right? So again, that's not a factor of safety. That comes from the von Mises yield criterion. The idea is that if I have a tensile strength of a ductile material, and I ask you what is its shear strength is about 60% of its tensile strength. Okay, so computing the capacity of a fillet weld. We have our phi value, we have our stress. What about our area? So how do we calculate the area? The area of a fillet weld equals the length multiplied by the throat. Okay? So, phi value is 0.75. Our limiting stress is 0.6 times the electrode. And then the area of the weld is the throat times the length, or 0.707A times the length. So that times that times that. That's how we compute the capacity of a fillet weld, looking at the weld node. Okay? Does that make sense? I think hopefully the point I'm trying to get across is that when we start using this on Monday, very plug and chug. Very, very plug and chug type expression. Not really difficult at all. Okay? All right. We'll take a step back, see if anybody has any questions. All right. That's the weld metal. What about the base metal? So the base metal says governed by J4. Okay? So let's talk about the manual. Okay? So chapter J is the chapter on connections, right? J1 is all the introductory material. What about J2? J2 is on welds. J3 is on bolts. What is J4? J4 is connecting elements. Okay? So if you look at section J4, you're going to see strength of elements in tension, strength of elements in shear. What is J43, by the way? Have we looked at J43 before? Isn't that block shear? We've looked at J43 before. So we've looked at this before because J4 is looking at the strength of the connecting elements. So in the case of a tension member, it was looking at the strength of the connection, but looking at the member, okay? So, so again, what's the deal with J43? We've looked at that before. Okay, we're interested in J42 because, again, we're assuming that our section is resisting elements or resisting load in shear. So we have two limit states: gross section yielding, net section fracture. Right, in this case, we're looking at shear yielding and shear fracture. So how do we compute the capacity? 0.6 FYAG, 0.6 FUANV. Okay? So gross area in shear and net area in shear. But the cool part is, because we're looking at a weld, okay, the gross area in shear and the net area in shear are going to be equal. Okay? Remember, how do you calculate the net area? You take the gross area minus the area lost due to the presence of bolts. We're talking about welds. There are no bolts, right? So there's nothing, we're not removing any material from the plate to deposit a fillet weld. So the gross area and the net area are going to be the same. And all they're going to be is the length of the weld times the thickness of the base metal. And that's it. So if you want a hashtag Instagrammable slide, this is the one, right? So we have, if we want to calculate the capacity of a weld, we say we have two limit states. We have weld metal capacity and base metal capacity, okay? How do we calculate the weld metal capacity? We take phi times our weld metal strength, which is 0.6 times the electrode, and then the area. The area is 0.707 LWA, LW being the length, A being the weld size. For the base metal, we say, all right, I have, for each one of these, I have a phi value. The phi value is different. 1 here, 0.75 here. So what's the capacity? 0.6 times either the yield or tensile strength of the base metal times either the gross area or the net area in shear. Okay? Does that make sense? Again, I'm hoping this is really straightforward. Let me take a step back and see if anybody has any questions. Everybody good? Okay, so I'm actually going to stop here, but I just want to give you a little taste on what we're going to talk about on Monday. So on Monday, so what I've talked about now is, given a weld, what is its strength? But there is more to it than that. There is the question of what happens if a weld gets too big or a weld gets too small, okay? And those issues are not directly related to capacity. Just like what happens if bolts get too close together or too far apart wasn't really related to capacity. It had other issues. Remember, if bolts get too close together, you can't get a wrench around it. If bolts get too far apart, you get water in between the connection. Same thing about welds. If welds get too big or too small, there are issues that aren't directly related to this. One of them, they kind of are, but not really. It's a little bit more closely related. But I want to talk about on Monday those weld limitations, then we'll do some problems. Okay? Sound good? Enjoy your no homeworks weekend from Steel Design. That's all I have, everybody. I will see you all on Monday.